So most of the panelists we've already introduced, but I also want to add comments about Gavam Shahidi, who was Dimitri's student, got all his degrees at MIT, and went to IBM and made SOI a mainstream technology. It's been around for a long time, and I think Gavam was a real leader in making that happen. And he's been Director of Silicon Research for up to 2015, our last 13 years or so, and now working on system miniaturization. So he's a wonderful person to have on the panel. Gavam, thanks. I just want to have a few slides on the panel just to get it started, and then we'll move on. So next slide, or sorry. Okay, so we know the panelists, all the invited speakers, and Gavam. And I just want to make a quick comment. You know, we talk about the future of nanoscale electronics and all the problems that are happening. Nothing's entirely new here. If we look at Gordon Moore's comment from 1965, he was showing kind of manufacturing cost versus number of components. And then if you try and do too much, of course, the cost goes up. So, you know, today's scaling challenges and opportunities were all anticipated, you know, 50 years ago. And he made the comment, of course, depending on the technology, it can be difficult to scale at cost. And we're saying that we're kind of going through the same thing again today. And also he commented that it may prove to be more economical to build large systems out of smaller functions, which are separately packaged and interconnected. So we finally come, you know, 50 years later to that conclusion as well. Of course, all along the way, whether from 1965 to when I started kind of at TI in the you know, mid 1980s, the end was always going to happen. So when I joined TI, this is actually, oh sorry, this is from a conference in 1986. That there was the half micron apocalypse that was supposed to happen. So it's not easy to predict the end. You know, no matter how difficult things are, it's always been difficult. And so the end was expected at the 500 nanometer node. And now we're at the you know, coming up to the 5 nanometer node. And of course, the issues are all the same. We can't get performance slow down, the cost is high. So it's true all the time. But you know, 20 nodes later or whatever, we've managed to get there. So the issue is what's happening next. But there was good foresight in this conference. In order to get beyond this roadblock, it was expected we go to 3D IC and you use innovative architectures and even AI. So that was the new wave of artificial intelligence. So 40 years later, we're back to the same point today. So I just want to get you know, what is the view you know, 30 to 40 years later from the panelists, and we kind of put together a few topics. You know, when's in terms of the end of 2D scaling, you know, kind of the when, you know, node in what year, and what's the main limitation, why will it stop, and what's the architecture and material that might show up at the end, and then discuss a little bit of the roadmap and economics of the 2.5D or 3D IC. Can all the Moore's law benefits still be achieved? Is there an easily defined scaling roadmap? Or do we just add new elements each generation? And what's the impact on the ecosystem? I mean, for the foundry and the supplier, as well as the customer. I mean, all the customers, whether it's auto or something, kind of depend on silicon technology, always improving, you know, every generation. But it's not obvious once we go to a 3D architecture, actually. And I think this came up earlier, is, you know, should technologists ride the wave of new applications or keep working on bottom-up technology development? You know, what should students work on? Of course, it's probably, it may be the same in my career, all professors follow the money, so that might be what it is. But I think there's a lot of work on both sides of the coin here. And then if the panelists have any comments, surprises in the past 30 years, and any surprises or predictions for the next 30 years, whether it's materials or physical properties or architectures in the future that might show up beyond what's been discussed. And with all of our great technologies, whether it's quantum computing and AI and all this next generation tech, and just if there's any comments as the view to the future, what's the world we're going to live in. So with that, I'll kind of start with the panel, and I do encourage people to ask as many questions as possible, and give everybody a little bit of a hard time. So. Well, there's it. So I guess I want to just start. The when, why, what is the end of 2D. So maybe I'll start with Gavam, who's been driving it for a long time. Let's hear his view.
First, let me divert for a second and just acknowledge that I think we are extremely fortunate to have been part of this scaling sort of revolution in the last 30 years. And even more fortunate that we have been students and colleagues of Portland and the others. And I myself have continued to interact with him over the last forever, basically. And I've learned so much from you, and I continue to learn from you, and I'm forever grateful to you. And thank you so much. Now, having said that, I have a more bleak view of what's happening. And basically, I think what is happening is that we went to the 3D devices, and they have, as Professor Antoniadis touched on it, they're high capacitance devices. And if I look at Intel's latest publication, 10 nanometer, basically compared to the 14 plus plus, there is 20% less current per actual fin width, and it has higher resistance, higher capacitance. So what it means is that it's a lower performance technology, and then it is a higher power technology. Now, for our industry, within at every 2-3 years, we expect a new node, and really the key feature of every node has been that the power per operation has continued to drop. And I think 10 nanometer, as it is right now, again, based on Intel's published device, the power is not coming down. I think if you have heard it, Intel yesterday announced that they're basically shifting the introduction of 10 nanometer devices to 2019. It was supposed to come 2017, then this year, now 2019. They even didn't say which half of the year, first half or second half. So it indicates to me that there's a fundamental problem that they're struggling with, and they claim is yield. I don't believe yield problems if a yield problem will be solved in 2-3 months, not a year. And it's more fundamental with power scaling that has ended. And to me, that ends, basically, it's the end of scaling. And I think it's going to force people to open their horizon, look at more structures and more materials. And I don't think it's fundamental, it could be, but I think basically we are at a serious inflection point for the industry right now. That, again, 14 could be the last node right now, as we stand right now. And that, to me, again, I'm sure with work we can overcome it, but not 100% sure. So this is something I think we're going to work at. So
just to make sure, Gavam, so in terms of the 14 nanometer node is in, you think the FinFET and silicon is the best way to end?
Well, actually, no. If you, again, look at Intel's sort of gain per node from 32, 22, and 14, historically, we used to get 70% drop per power at every node. 45, 32, drop per power per operation, energy per operation, dropped to 50%. 22, it went down to 30%. Initial 14, at high frequency, there was no gain. Actually, the power had gone up slightly. 14 plus and 14 plus plus brought it down to 25%. Now looking at 10, initial 10 data indicates the power is going up. So I'm not sure, I could argue that maybe lower capacitance devices were in a better path, but again, we are where we are right now. But the question is how you will move forward, and is there an potential issue there or not?
Okay. So Philip or Paulo or Lisa, maybe have a comment on kind of the why it's, what's the reason for ending? Do you ever agree with the Gavan's power, and is it ending now? And Philip, maybe you can add a few comments.
Yeah, sure. I always agree with my former colleague, Gavan. It is true. If you look at the real hard data, the Gavan has mentioned that what Intel showed or what other foundry like TSMC and Samsung showed, 2D scaling is slowing down. But that doesn't mean the end of the world. The fact that we have historically obtained all the benefits that we have, cost reduction, power performance gain, and so on, through two-dimensional scaling, doesn't mean that we have to continue to use the same trick going forward. I think there are many other tricks, and like Lisa just talked about, multi-chip packages and so on. 2D stacking, 3D stacking, all kinds of stuff that we could do to continue the performance gains and cost reduction that we have had before. And the fact that we have lost one knob out of so many knobs, I don't quite care.
Yeah. but in terms of the end of 2D scaling, I mean, should we stop at FinFET? Should we keep going to gate-all-around devices? You know, Samsung has announced that 7-nanometer nodes. I think other companies might have as well, of course. So it hasn't ended. I mean, people put billions of dollars into 2D scaling. So that's my question. I mean, do you think the end is a 7, 5, 3, or and maybe I'm curious what architecture? You talked a lot about different gate-all-around devices. So do you think new materials? So I'm kind of curious the when do you think it's going to end, and what's the structure that will be at the end of 2D scaling?
That is harder to predict because it's always a kind of optimization function that you need to work on, how difficult it is to do something versus how much gain you get doing the same way that you have done before or try something else. Right? And also it's a function of how mature that something else that you're jumping into, and when you decide to jump ship, it's not quite clear. Right? So
that's the professorial answer. No.
Hey, I'd actually like
Lisa, go ahead.
I'd actually like to hear Paolo's answer.
Yeah.
So, Lisa, you missed my presentation. So I showed 1998, when I put together the program, that showed something that looked like a coaxial cable. But I said, until 2020, we're not going to be able to make this kind of structure. So I see the, FinFET was just one step towards the kind of structure. And the ultimate structure we've always known is something where you can control the fully depleted structure. We had disagree how to do it from a technology point of view. But topologically, whether you do it horizontally or vertically, we were going to end up with the structure anyway. The thing that is beneficial is if you know what the end is, you don't want to run it to the very end, but you want to make your change as soon as you can. So switching to a completely vertical, fully surrounded transistor, the sooner we can do that, the better it is. Because then we can really try to learn how to make multiple layers of this transistor and stack, besides transistors, trans, all the different kind of memory on top. So I see this more, inertia. It's easier to say we're going to do, 10 nanometers, 7 nanometers, 5 nanometers, I explained today, that to go to your boss and say, I think we should do something vertical that is very risky from your career, because you're telling me that we have to do something different. So I think I would have stopped at 10 nanometer. There was no reason for me to go to 7 nanometer or 5. It would have been good to start already there. The fact that the memory guy got it in 2014 shows once again that we let him do all the work and then we take the glory. That is typical approach in the industry, okay? So I don't think the migration to vertical structure could happen any time. It just in this moment, TSMC, Samsung, and Intel are saying, who's going to do it first? If you go back to 2000, what happened? In 1989, I wrote a paper with Gelsinger that says, around 2001, we're going to run into power problems. So we should go to a 4-core arrangement and cut down the frequency. Well, nobody blinked until in 2003, finally Prescott got to 130 watts. And then overnight, AMD and Intel changed to 2 cores and then 4 cores. So it seems that the industry, instead of being proactive in making a change that is very clear what it should be, waits until you crash, and then you do it as an emergency. So in my mind, already 10 nanometer, 7 nanometer was already a good ground to begin doing vertical structure. But due to the inertia of the industry, probably we're going to run into 5 nanometer and have a major disaster. All the stocks crash for 6 months, and then I buy. And then in the next 12 months, it gets implemented. I have a company to my far left that I bought a few dollars. Thank you very much, Lisa. Thank you. Okay? And I don't know if you noticed, the SMC is $38. I bought that too, okay? Sorry.
Well, you can start your investment newsletter, but Lisa, maybe come back to Paolo. But are you planning on architectures? I mean, with your technologists, with vertical devices, or do you?
Well,
There's quite a
actually-
disparity of opinion on vertical devices up here, I'm sure.
No, what I wanted to do is I wanted to record Gavam and play him, like, for everyone to say that 10 nanometers is the end. No, look, I don't,
Looking at Intel's FinFET bulk. So
and by the way, I'm okay with that, okay?
That device is not scalable because it's basically 14 plus plus. The sheet of FinFET is high resistance, high capacitance, and lower drive current. I mean, that device is not going to make it. You can record me on that, okay? So.
Okay. Gavam Shahidi says, no, look, I think we have a lot of different levers to get where we need to go. By the way, I do think the foundry roadmap is pretty strong, so I will say that. I spent a lot of time at IBM, certainly have a lot of respect for Intel's technology, but one of the things that you find is when you have foundries who really service hundreds of customers and many different applications, they optimize for a different thing, and so I think there is some improvement yet to go, and I think 7 nanometer is actually a great node. I don't know about 5, but actually I agree with Paolo. I think that there is something to be said about being proactive and not waiting for the disaster to happen before you switch. I mean, we spent a tremendous amount of time actually trying to decide, would we really go heavily into multi-chip modules, because hey, it's much easier to follow sort of the regular scaling path. And the answer is, this thing just looks like it will be very, very expensive and not really return. So I agree. So let's decide how we do that. But I think as an industry, the more we're able to trial these technologies in smaller volume applications, I think the better. So.
Okay, so there's vertical, there's kind of 3D stack, and we can kind of discuss that next, but I'm just kind of curious on the vertical, because you're really looking at vertical GAA devices, well, whether it's a sheet or a wire, and so one issue is, do you think you can really hit all the performance expectations at a vertical device and scale cell area with a vertical device? I mean, we have to start kind of with a 2D structure in vertical, but your W effective of a vertical device is limited by cell height, and kind of your mechanisms of strain are maybe not there, and your interconnect architecture is a little bit difficult. So even though it sounds good, I mean, everybody's looking at it, and with different opinions, I think. But why do you think it's the absolute best thing to do? I mean, as opposed to stacking up another type of device on top of each other, or stacking, wafer stacking or something of another device. Why does it have to be a vertical GAA device that you think is the best device to start stacking up on?
So I didn't get time. Unfortunately, the clicker wasn't working properly, okay? What I wanted to show you, I took the 7 nanometer TSMC memory cell. Mm-hmm. And you can look at the number that was presented at ADM 2016. Mm-hmm. And it was 100 by 250, okay? So I extracted all the design rules, and then instead of laying it up in 2D, using precisely the same design rules, I designed it with 2 transistors, one stacked on top of the other. And the size of the cell is about 110 by 110. Mm-hmm. So, but in this case, I had actually 8 transistors as opposed to 6. So with the same design rules, the benefit was 40% size for the cell. Mm-hmm. So that by itself buys you,
So when you consider vertical, you're considering like N over P or P over N or something.
Yeah, so
not so much a vertical N, vertical P.
No, take for instance, if you look at the layout of a cell, okay? Mm-hmm. There are 2 major limitations in the memory cell. Mm-hmm. The first one is that you have to have an N channel, an N well, something of this kind. So when you look at the spacing between polysilicon lines, it should be like 20 nanometer with the 7 nanometer design rules. But since you have a well, it becomes 40 nanometer. Okay? In the moment you put it up, it's very easy, to dope NP, NP, or even during deposition or whatever it is. So the weld disappears. And so you save 20 nanometers right there. So if you look at the design rules and what it does, laying up things vertically, there is so much benefit that you should be encouraged to aggressively try to do it.
So that's for regular SRAM, but for irregular logic, do you see it as a problem in terms of interconnects, or you think there's a new logic architecture to take advantage, or?
No, what I showed it was the universal layout. Once you have transistor, the basic ingredient, whether it's for logic or memory, is an N channel and a P channel. How you connect them then decides where you go. So once your basic building block is like an N channel and a P channel on top, then the interconnect decides what you design.
Okay, let me just make sure. So your focus is N over P as a vertical structure. But you had talked about, I just want to make sure, a vertical GAA wire for each N and P.
Yes.
So do you think that each N and P should be a vertical device, or could it be a horizontal device stacked on each other?
I think if you do the transition, you may do, right now people are chickening out and doing all in this way and slowly waiting to eventually do this. That is okay, you do it in steps, right? But eventually, if you had one on top of the other, fully round in this way, and when N on P, that's a building block, and then the interconnects, it's like an ASIC. Then you decide, if you want to connect in this way, it's a memory cell, or you connect more of them, you make a logic node, or whatever.
Okay. So your main
That's my take.
Your main constraint is area, and then okay. So I guess, does anybody else have any other opinions?
Let me just ask Paolo to elaborate a little bit. In that idea of yours, where you have this kind of vertically integrated CMOS inverter with a nanowire as a channel, what about W scaling if you need to drive, a little bit more current?
So one of the things, again,
stacked up in parallel?
No. So actually, if you look at what they're doing right now, okay, I'm sorry because you went too fast. If you look at right now, the way the current is increasing by increasing the height of the fin. Okay, the fin began 34 nanometer, went to about 43, and then it went to 53. So now it was in this way, right? So now what you're doing, you're turning on the side. So what you have something that is maybe 6, 7 nanometer, but you adjust the length. Okay. Like I said, essentially like a sheet, right? So since you already only have a cell that is 40% of what it was, you can use your 401k and spend it back in making them longer and get more performance. With this, if you make all the carbon nanotube work, the better, okay? They're much more efficient. But this, I'm just taking the very conservative approach. Instead of making a FinFET in this way, make it in this way, make it longer. And the gate, remember, right now your gate with the line edge roughness is between 10 and 15 nanometer. Ask a designer, how am I going to design something with this, right? But if you make it vertical, there is 10 nanometer plus or minus 0.5 nanometer. These are two low-hanging fruits in my mind, okay?
But I think your comment is a good one. I mean, this is the kind of the fundamental problem of vertical devices is the cell area is limited by the W effective of a vertical device. Okay, so I think we'll stop on this. I guess the net is Gavam, there's a camp that sees it ending now, and there's a camp that Apollo says almost unlimited. Go to vertical devices, really stacking N over P. I'm still not sure if it has to be a vertical device, but I think that's your comment that we're limited by area. Things should happen now. I'm a little more optimistic that there's maybe a few more in a planar architecture, but there's a lot of work on all different architectures ongoing, whether it's lateral, vertical nanosheets, and the same with nanowires, and also FinFET perturbations as well. Okay, let's if there's no other kind of arguments to that,
I do have a question
Okay.
or a comment.
Go ahead.
Thank you. I mean, I really like the vertical architecture. I think that has a very interesting opportunities, but at the same time, if we don't continue the power scaling, we will need to find a way to get rid of the heat. And you need volume there to be able to dissipate the heat. We could think of having layers kind of interposed in the chip to remove the heat. But if we need those thermal dissipation layers, how would that be different from wafer stacking, in the sense that we are going to have a few transistors stacked vertically, then a thermal layer, and then the idea is to stack more wafers like that, one on top of each other? How are we going to get rid of the heat in the vertical architecture?
So this kind of goes into the next thing, which is just, you know, the feasibility of 2.5D, 3D economics.
So if you guys pay attention to Philip's sketch, he has very clear layers that are for heat dissipation, right? You have to have these layers, okay? But they're relatively easy to deposit, okay? Because essentially, it's easier to program, you know, something that deposits different layers than to put a $150 million, you know, EUV machine that Tony sells very happily, you know, and so you can buy 10 deposition tools with the same amount of money, okay? This is strictly economics, okay?
But the processor burns 100 watts, 150 watts. How can I take the power out with the sheet? You have to have a big thermal thing on top of it to get all the heat out.
So these people at IBM show me these 350 watts, you know, they have this cooling and so forth. So we need to define, first of all, what is the business driver in this moment? It's the data center, right? It's a gold mine, 80% margin, right? Yeah. So you can do all this stuff in the data center. So Telco already, look at the revenue Intel announced. So look, you know, I bought it, you know, 40, 50% is in the data center. That has been a gold mine.
But if you stack chips, how do you want to take the heat out of a 100 watt or 200 watt chip?
Those are then you have to look at how much you need. Remember, you go back, how much do you want the client to be powerful? We are going back to the mainframe, right? You used to have a mainframe in the basement. Now the mainframe is in Alaska, but we are back to the same scheme, right? You do everything remotely and you fool everybody, say, oh, we got a new scheme. Because of the internet, you look at the mainframe and it says in the cloud. It's not in the cloud. It's 100 megawatts object in a cold place that used to have in the basement with 50 programmers doing it for you, and these 50 people are selling your data to somebody else. So good luck, okay? But it's a model, okay?
So besides heat, though, in Lisa and Paolo and some of the others on the photonic side, what's the roadmap for 3D? In other words, we're talking about, okay, there's photonics, there's, you know, maybe there's some AI, there's sensors, power management, memories. What's the easily defined roadmap for customer or tool vendors to follow? Or is it, you know, kind of, is it a one-up each generation? I mean, I guess in Paolo we just keep stacking N and Ps. I'm not sure how, but we've also talked about a lot of different functionalities. So the whole ecosystem is based on performance boost per generation, you know, from scaling. Now we're talking about all these new elements going into 3D. How do you see it working? I mean, how does the customer get prepared?
Well, I'll just make one. I won't answer the general question, but I'll make a comment on functionality since you brought it up. Mm-hmm. I think there are, you know, at least two functionalities that are becoming, you know, absolutely essential. One is pervasive encryption, right? So if you look at, for example, the latest release of our mainframe, one of the selling features of it, and it's been enormously successful in doing that, is that you can process the data encrypted the whole time, like you never can get it out. So I think we're going to see, because of the comments that were made before around security and so on, the desire to have an all encrypted all the time operation will be fundamental. So that's one function that will be essential. And I think the second one is the whole aspect around machine learning and classification, right? Dedicated functions to be able to do that extraordinarily efficiently, right, and scalably would be two characteristics just because of the sheer number of applications and requirements that will be needed. So at least those two, I think, will be fundamental in all functions.
Okay, but do you see that as being needing a 3D architecture, or that's just a?
It could benefit from it. I don't think it's just,
It's needed, right.
I think it's just a function that is going to be needed already
Right,
in the person
right.
2D. But I do think that there'll be big
those-
opportunities that can happen with a 3D.
That's
as
right.
well.
But still, if we go from, like I say, all the customers have depended on this 2D scaling, the performance boost per generation. But I still am curious on the 3D architecture, and we have all these different elements. What is the roadmap for performance boost per generation with all these new technologies coming in? I'm kind of curious. Maybe, Philip, if you
It's
have a
interesting
comment
you
to
talk about a roadmap. Everything is on a time horizon, right? So at a university, you can talk about visionary thing that happens like 50 years later, but everything happens in a time horizon. So having sort of like a vision of the roadmap is important. Today, if you look at performance, like broadly defined, either speed and latency, power, energy, and so on, whatever way you want to define it. The most important thing is memory access, right? So getting the memory on chip closer and closer to the processor, closer and closer to the accelerators, closer and closer to whatever you do the computation on is the most important thing. So if you ask about what is the roadmap for continual performance improvement, performance broadly defined, is getting the memory on chip. That's the most important near-term thing. And you see the handwriting on the wall. AMD is putting multi-chip thing, putting all the memory HBM chips is one example of that, right? So DRAM is slow. We want it faster. We'll stack them together and put a logic chip together. So these things are happening already, and see the handwriting on the wall that more and more connections closer and closer to the processing.
So that's kind of your performance boost per generation will be
exactly,
from
that requires
memory latency and
right.
and memory density.
Yeah, that's right, and that requires the industry to think about technology generation in a different way. Right? We tend to think about technology generation as saying 10 nanometer is better than 14, 14 being better than the previous generation, and so on and so forth. These numbers denote not only advancement in technology, but denote some advancement in some kind of a goodness, right? And the goodness today, well, has always been what the customer actually see, what the system, what the complete system sees, right? So this already show that the technology piece is 40% of the whole stack. Right, so if you think about a whole system, you think about what the technology provide that will give the system level performance increase, not just that particular tiny transistor provides.
So we kind of say, the industry, you have cost per transistor and you have power production per generation and meeting performance. I guess what you're saying is that, well, if we just stack memory up, a 3D roadmap for memory, we should be able to continue that, effectively that Moore's law of economics. Is your view?
Even without the traditional metric of two-dimensional scale.
I see. Okay. So
in
Lisa,
other words, the metric by which we gauge progress is out of date.
I see.
Yeah, I think I would say perhaps something like this, which is the overall metric for the industry that's important is still something around performance per dollar or performance per dollar per watt. Now, how you get there, whether you get there through, more 2D improvements, or 3D. I happen to agree with Philip very strongly that memory is a big piece of it. Whether you integrate power management or you integrate XYZ, whatever, are you getting yourself above that performance per dollar, or are you below? Because if it's below, nobody wants to take that. Why bother, right? It's just too much risk. It takes too much time. But if you can show something that gives us an inflection point that goes above the traditional curve, then that's worth it. That's worth taking the risk. That's worth the industry spending all that time to move that technology forward.
So in terms of, I guess I'm curious, like photonics or GaN, is that part of that 3D infrastructure, or?
If there's a way for it to be above that curve, I think somebody will absolutely use it. Now, if it's so expensive that it's below that curve, then, maybe not.
I see. So, and then maybe Jason, if you have any comment or?
Yeah, I guess I can make a comment. I wouldn't necessarily always tie photonics to 3D. 3D is an implementation, but I would just kind of abstract it up a little bit to the problem of interconnection of high density at low energy. And so one number that really struck me that I haven't been paying too much close attention to since I was at MIT is exactly where the energy for memory communication is today. You had 3.5 picojoules on your slide. If like we were writing DARPA proposals in 2011, and I said that 5 years or 7 years from 2011, we would be at 3.5 picojoules per bit, we would have been harassed by saying that we were being way too conservative on electronic progress. When we were road mapping what the impact of optics would be, quite a while ago, we were looking at 1 picojoule per bit in 2015 for a high density, high bandwidth communication link. And even that was being criticized as being, oh, you're not giving the electronics community enough credit. I think that the electronics community, I give a ton of credit, but we need to be realistic about the problem associated with interconnection and be open to solutions. But generally with photonics, you need an entire ecosystem, and it's actually that per dollar aspect of your comment on how do you have a solution that has the communication bandwidth and density for a scalable, deployable dollar figure that could lead to an adoption trajectory.
And then maybe one last question, as we'll move on. In terms of the 3D stacking, is it wafer stacking, monolithic 3D, or some other approach, maybe Lisa, that you see as the most viable?
I think there's still a lot of work that's going on in terms of how it comes together. And as I said, I think the issue is not what is technically feasible. There are many, many things that are technically feasible. It's really what's manufacturable in the environment.
Okay. Does anybody else have any other comment? And otherwise, we'll move on.
A brief comment,
Sure.
if you don't mind. I mean, I think it makes a lot of sense to move from a technology-focused roadmap to a system-focused roadmap. But at the same time, we are losing something really important in that transition, which is what is going to happen with systems that we cannot even think about right now, completely new systems that are not in our roadmap. When we focus on the technology and Moore's law and scaling and so on, we had entire industries that were riding along the semiconductor industry, and we wouldn't have low-cost DNA sequencing without Moore's law and so on. My fear is that if we identify 3, 4, 5 systems that we know of today, and we say, okay, for the next 20 years, for the next 30 years, let's optimize those systems, we may miss opportunities to create completely new fields.
Right.
And that's something that I am worried about.
Okay, so that kind of goes into what the third topic. Should we ride the wave of new applications or new proposed new systems that we see coming up, or focus on bottoms-up technology development? Your comment would be to focus, or at least don't lose sight of bottoms-up technology development. Yeah, sure.
I just wanted to point out something that I've been thinking about a bit for a while. In this discussion about conventional technology, dimension scaling coming to an end, and so forth and so on, and we all think about the impact of that on the technology and on the customers and so on and so forth. There's another impact. There's an army of engineers who are currently working on that problem. And if that problem comes to an end, then there's a huge reservoir of talent to work on, for example, yielding that 3D chip that Philip showed us. So, or figuring out what's the best way to put these different elements together, spreading the heat and so forth. And not just those engineers that are in some of the companies represented on the panel and other companies that are not represented here, but a lot of the university academic community and the students and so forth. So something else that particularly some of you industry leaders might be thinking about is how we're going to best capture and make effective use of that fantastic talent reservoir. We shouldn't let that dissipate. I think that could be an important piece of how we're going to figure out how to drive this entire enterprise forward.
I think well spoken. Okay, Tony?
I will reply to Paulo's comment of not needing advanced lithography for 3D, that's not true.
Heresy for ASML.
Exactly. We only make one category of products, but this is not 3D NAND. 3D logic, every layer you still need to connect from a gate to gate, a source to a source, a source to a drain. So fine lithography is still needed. That's all.
Well, that kind of goes back to how do you interconnect everything. So yeah, we want to keep ASML in business certainly for a while. So. Yes, you do. No. I mean, I have to support Tony on this one. So the kind of two smaller topics, but if anybody has a comment on, I don't know, maybe surprises in the last 30 years, the end was always near, and maybe we're saying the end. Here's the end, but is there any surprise coming up in the next 30 years that somebody sees?
Well, you'll never know where the surprises are, otherwise you won't be surprised, right? So, but if you look back, not too far back, right, the surprise, well, we always say, silicon is a magic material, silicon oxide, and so on, this magic material, we can use it for everything, right? But it turns out, it looks like we have a new magic material, that's hafnium. I remember back in the late 90s when I was at IBM, I was, working with people to come up with the next high-K gauge dielectric, and everybody talk about aluminum oxide, zirconium oxide, and so on. And somebody stood up and said, "What about hafnium oxide?" And everybody looked at him and said, "What? Where is hafnium in the periodic table?" Nobody knew what hafnium was. So, but now hafnium is in all the high-K gauge dielectric. Hafnium oxide is also in the resistor switching memory that actually switch many times very reliably. And if you dope it with zirconium or aluminum, even dope it with silicon, you can have ferroelectrics. You can make negative capacitance transistors. You can make ferroelectric memory. You can make lots of stuff with hafnium. So it turns out hafnium is a big surprise.
But it's rare.
It is rare, but not rare enough to prevent us from making chips out of it.
Steve?
Being used in optics long time, actually.
Right.
It's a coating material because it's very hard. So I want to make a few comments, I think. Remember one, I think the innovation never ends.
Right.
So anybody say it's going to end is going to be wrong. Right. So to contribute, Dimitri, I want to tell you a real story. 85, we made 60 nanometer channel MOSFET and sent it to IDM, which was over 10x smaller than the Unitrip. And the paper was rejected. The reason, industry never going to get to that small. All right? So I think all the naysayers are going to be wrong because anything have plenty of room for the development. For example, the bicycle, right? The simplest device. But today, still many new things being developed. So what determines going to continue to develop or not is, as Lisa said, is the price. But is the demand and price. Is there a need? People pay for it. If there's a need, new things always come up. So I always encourage my students that don't believe the naysayers. The innovation is endless.
Yeah, I agree, and that's kind of the point. Like when I joined TI, a tremendous number of papers saying the end, multiple years, and then it stopped. Now we're kind of back at 100 nanometers, factor 100 lower. It's the end again. At some point, you're going to be right, but I agree with you. Innovation always seems to happen.
I don't believe a particular approach
Mm-hmm.
will be the answer.
Right.
There are many factors.
Right.
Maybe one day the lithography becomes so great, right?
Right.
Or there is another materials, there is another ways. So just people extremely intelligent, and the new innovation will come out.
Right.
So let me give you another story of encouragement. In the last 3 years, I wrote a paper where I calculated all the benefits and so forth. but you send on 3D, you sent this paper, without the name of the author as a blind, and he came back, the author obviously doesn't understand Moore's law, okay, and got rejected. So I'm on a good track. I know for sure that this is the right thing to do, okay?
Yeah, go ahead, because yeah, especially.
So, yeah.
Okay, we're gonna finish this out.
All right.
Maybe next a few minutes, and then go ahead, Bert, please.
So Mark, you asked about surprises we might foresee, and
right.
It's impossible indeed to predict the surprise, but they often can be found in where you don't know something, where there's known unknowns.
Right.
Right.
Uh-oh.
And I think, there's a lot of those still out in the materials side. For example, Dario talked about that these quantum computers that IBM is building now are being used to simulate small molecules. That's the first step. Mm-hmm. As things become bigger and you have correlated quantum materials where superposition and coherence play a major role, it's still impossible for us to predict the properties of these materials. And I think one of the most amazing things is probably high temperature superconductivity. You have a material that at room temperature is a lousy conductor, but if you cool it, it becomes a superconductor. We don't know, and it's been 40 years, but we still don't understand the workings of it. Mm-hmm. But just recently, for example, and the group of Professor Pablo Gavrilo Herrero, they realized exotic superconductivity in some very reductionist, just purely carbon materials. Mm-hmm. At the same time, some of the quantum computers are getting to the point where they can predict materials, even without error correction and so on. These are imperfect quantum computers, where maybe the errors actually factor into coherence as a benefit. They can predict these mid-scale many-body quantum materials. Mm-hmm. Mm-hmm. And so I think someplace where I think there could be some really amazing surprises is getting to a point where we have a tool, maybe a bit like the Supreme or the Centaurus software package, but for predicting quantum materials that will allow us to first understand the physics of them and then develop new ones. And then that would have a huge impact. If, for example, we had a 200-degree Kelvin superconductor or something like this, it's not out of the question. How would that impact all of these?
Well, then we could stay with silicon and use that interconnect material, and that would be good. So maybe that's the big surprise. I guess in the past, power has always been the driver. At some point, power gets too high. You have to go to a new technology. So we'll see what surprise comes up. But I agree with Steve. Innovation always happens. Don't limit what's going on. There's always a little bit of a surprise how long things last. But I'll be curious on the materials as well. I think that's the promise of quantum computing, the quantum simulation. So, okay, I guess in the end we've said, I don't think there's a unanimous, but I think everything's coming to the end fairly soon. And we'll go 3D. And maybe some new material surprises. Okay.
All right. We're 2.5 minutes over time. Okay. Thank you all for the panel. Okay. The next thing we're going to do is have some remarks from Dimitri, but that's going to be followed by some photography. The first thing we want to do is have Dimitri with his former students, postdocs, and visitors. Okay, over here, I guess, wherever Paul wants to do it. And then would like to get a photo of everybody together. And that's up to the photographer and how to do that one. So Dimitri. 3 minutes. It was only 3.
Well, I expect I will catch us up. I don't want to take very much time. This was, you can't hear me? Yeah. This was really a great occasion for me, and I hope that you all had the chance to enjoy the back and forth and the many presentations, the panel, and all that that happened today. I have to say that I'm humbled by all the attributions and acknowledgments that I've heard of my work. It was interesting to
be reminded of some things that I have had myself completely forgotten. I think what comes out of this very interesting discussion today is that you ain't seen nothing yet. And there is tremendous potential in electrical engineering, in computing, in a multitude of applications that are touched by electronics and microfabrication in general. We may argue, and there will be certainly good arguments for what device architecture, interconnect architecture, overall architecture of the technology is going to be the one that moves forward. But I think we still can see that the way forward is there, and it's all in front of us. I had been lucky to work in this field at a time where quantifying the performance of what I was working on, which was the high-performance transistor, was relatively easy, okay? And you had to improve the transconductance of the device, and you had to make sure that the capacitance was not rising too rapidly. Clearly, we're in a domain where this is only a partial metric because of the fact that the Moore's law is much more generalized, well beyond the Dennard kind of scaling. So, but I think the fact that things are getting harder to quantify or maybe harder to even evaluate doesn't necessarily mean that progress is not going to happen. In fact, we have produced a lot more brilliant talent, as Jeff said, that is ready out there to tackle the next generation of problems, and that is going to happen. And I think the future is really very bright for our industry. So thank you all for coming today. And again, my deepest gratitude for those that worked very hard to put together this event. Thank you.